is a recording about electromagnetic induction. We're going to go through Faraday's law and Lenz's law, and then there will be one more video to cover inductance in a circuit and like LR circuits. So inductance is, let's start here. If you have a changing magnetic flux, then a current will, or a voltage, an EMF, will be produced in a wire that will try to kind of fight that changing magnetic flux. It tries to return the magnetic flux to what it just was. So inductance basically is trying to keep things the same. So up here we have, if you have a coil of wire here and you move a magnet through it, and you change the magnetic field and you change the flux that's going through that coil of wire, that will create a current in the wire. And the current will then create a magnetic field which will try to oppose the changing magnetic field. So again, this negative d whatever theta flux dt, the induced voltage, the induced EMF, is going to be trying to keep the magnetic flux constant. It's not related to necessarily just the value of the magnetic flux, but the change of magnetic flux. So let's see if I can come over here. So here we go. An EMF can be induced in a circuit in several ways. The magnitude of B of the magnetic field can change with time, in which case a current will be introduced in the wire. An EMF will be introduced into a wire that will kind of try to balance that. An area enclosed by the loop can change with time. That would also change the flux. The angle theta between the magnetic field and the normal to the loop can change with time, and any combination of the above. So if there's a changing magnetic flux, it's called a back EMF, or an induced EMF, will be produced to try to keep the magnetic flux constant. So here we go. A circular loop is held in a uniform magnetic field with the plane of the loop perpendicular to the field lines. Which of the following will not cause a current to be induced in the loop? Crushing the loop, well, that would change the size of the area, so that would change the flux. Rotating the loop about an axis perpendicular to the field lines, so that would change the magnetic flux as well, because it would change this angle. Keeping the orientation of the loop fixed and moving it along the field lines, that would not change the magnetic flux because it's a uniform magnetic field, so you'd just be moving it over. Or pulling the loop out of the field, again, that would change the magnetic flux, and so that would change it. So the answer is C. Okay, now applications here. Let's actually, how many do I? No, we're good on those. All right, so motional EMF. This is saying that if you have a current carrying wire, or like if you have a charge here, and it's placed in a uniform magnetic field, then you will develop an electric field as well, an EMF from one side of this to the other. So again, a straight electrical conductor of length L, it's actually moving, it does have to be moving in the magnetic field. It's moving with velocity v through a magnetic field directed perpendicular to that velocity. If we're going to use the right-hand rule, it should make sense to everybody that you've got a magnetic field that's going into the page. You have a velocity that's going to the right, which means that the magnetic force should be going... Oh, that's an electron. So since this is an electron, that magnetic force should be going downward. And the electric force would be going upward, because your electric field is going to be in this direction. It's going to balance that. If you're in steady state, the conductor is balanced. You've got the electric field equal to, the electric force equal to the magnetic force. And we've seen that in a velocity selector already, that same kind of correlation here. But due to the magnetic force on the electron, the ends of the conductor become oppositely charged, which establishes an electric field in the conductor. So the electrons move and you establish an electric field. And that electric field also means that there's an induced EMF there. This is one that I really want to talk about. If you have, okay, this is a circuit. Do y'all see this circuit? But instead of having a wire here, you have a conductor. And this conductor is moving with a constant velocity to the right. Again, our magnetic field is going into the page. Our conductor is moving to the right. And so the force that would be experienced, again, magnetic field to the right, you would start to send the current this direction. It would be moving through here. But if this velocity is moving over here, then the area enclosed right here in this square is changing. And if you're changing the area, you're changing the magnetic flux through that area. And so you will develop a magnetic force on the bar in the opposite direction of the applied force. Again, our flux was BLX, again, magnetic field times the length of this wire here times this X. But since that X is changing, it's this X, dx dt is your velocity. That means that you have a changing magnetic flux here. And if you have a changing magnetic flux, then there's an EMF that's produced that has a value of negative BLV, because it's the change of the magnetic flux divided by time, and this x dt is velocity. And so you produce a current based on this voltage here. That's where you get your current that is running through here. So instead of having a battery as your source of voltage or as your source of EMF, electromotive force, you have a moving bar. And that moving bar is going to create a current that's going to go this way. And that is your induced EMF there. In terms of calculus, this is going to look really similar to kind of terminal velocity problems. Let's read the problem. So find the speed of the bar as a function of time after it's released. It's released from rest. No, it's actually given initial velocity. Excuse me. It has to be moving for you to have a magnetic field at all. Magnetic force at all. So again, it starts moving. And we have our magnetic force is negative ILB. Again, that was IL cross B. It's just the formula for the magnetic force. Magnetic force is moving into the page. And this is because the current that's induced, the current that runs through here, ends up going from the bottom to the top. And the reason that the current ends up going from the bottom to the top, creating this magnetic field, is that you create an induced EMF here. So again, we've got F equals ma, and so our force, which is our magnetic force, which is opposing the velocity of this, is m dv dt. And our magnetic force, this is our current. Our current is an induced current, and that's caused by that induced EMF. And that we just went through how we're getting that induced current. We have an induced EMF because of the movement of this over to the right, of the bar to the right. So this is the current. This is I, the induced current, divided by R. Induced EMF divided by R, times the length and times B. When you put all that together, you get all this stuff. Move the velocity to the other side, integrate both sides. You get this ln term. There's nothing over here except for time. And you're left with the speed is equal to the initial speed times e to the negative t over tau. And that tau is that big old thing. If you have a rotating bar, it's going to be very similar, except it's got an angular velocity. Actually, I'm not going to worry about that one too much right now. Let's see. So this is where it gets really cool. So Lenz's law. So Faraday's law says that a changing magnetic flux will produce an induced EMF that will then try to counteract the change of flux. But Lenz's law really talks about the direction of that induced EMF. The induced current in a loop is the direction that creates a magnetic field that opposes the change in magnetic flux. So basically, inductance is like a little old lady trying to keep things the same, doesn't like change. So if it changes one way, it's trying to return it to whatever it was. So the current that's induced in a loop will be induced in a direction that would create the opposite magnetic field. So again, if the object, this bar, was moving to the left, well, that means that you were increasing the magnetic flux because this area was increasing, which means you want a magnetic field to go in the opposite direction. And so if your velocity is to the left, well, I'm sorry, you want to create a magnetic field that would come out of the page here because you're increasing the magnetic field that's going through this area. So you want a magnetic field to be created that would come out of the page. If I put my thumb pointing up this direction, my right thumb, I want my fingers to curl around the back of that bar and come out right about here. So my fingers would wrap around this way. And to do that, my thumb, remember, is the current. So the current would run this direction. But however, if you were doing this and you're decreasing the area of this box, then you would be decreasing the magnetic flux through that area. And so you would want to increase the magnetic flux, which means you would want to add more magnetic field or magnetic force going into the page, which means you would want a current to run this direction so that my fingers would loop around the back and come out here. My fingertips would be here if my thumb was on this. So run that way. So here, this is where it gets into Lenz's law of the directionality. So this shows a circular loop of wire falling toward a wire carrying current to the left. What is the direction of the induced current? Well, this current is going this direction, which means that the magnetic field at this, like right above it, because of that, is going into the page right here. That means as this approaches, it's getting more more magnetic field going into the page, which means it is going to try to induce a current in this wire that would try to come out of the page. And if I'm using the right-hand rule again, if I want the current to come out of the page at that point, then my finger needs to go, let's see, this one went there. So you want something that will come this direction. Earlier I had it worked out counterclockwise. I'm trying to figure out. That's going into the page. So I want to make more out of the page. And if I want more out of the page, then the current's going to run this way, which means my fingertips would come out of the page in the middle of this circle. Right, because you're getting more of it in the circle, you're getting more into it as it falls. Same thing here. If you are increasing the magnetic flux by moving this magnet into here, then I want to decrease the magnetic flux. So I will create a magnetic flux. I'm going to try to create a magnetic field that would run this way, which means my current needs to go that way, so that my fingertips would go through the center and back to the left through the center. If this was increasing, I want to create a magnetic field that goes in the opposite direction, which is why my current runs up there. If you are reducing this magnetic flux, in other words, you're pulling the bar magnet out, then you want to create more magnetic field going in the opposite direction. And so you would have this clockwise sort of motion, current going there. That's a lot of right-hand rule stuff. And this example is really good. So you have a rectangular metallic loop. It's L versus W, length and width. It moves with a constant speed through this magnetic field, which is 3W long. So what happens to, let's see, we want to know the magnetic flux through it, the induced EMF, and the applied force. So the magnetic flux is going to increase, increase, increase as it moves in, and then it'll all be inside, this whole thing will be in the field. So you'll have a constant magnetic flux. And then as it's coming out from here to there, you would decrease the magnetic flux until it was zero again. Well, the only place where the magnetic flux was changing was right here and right here. And so that's when you're going to get an induced EMF. The induced EMF here, since your magnetic flux was increasing, this induced EMF will be negative to try to decrease that magnetic flux. And here, since the magnetic flux was decreasing, you will create a positive induced EMF. And the force, since it squares out, is positive for both. So again, same sort of thing. This is saying the electric field, when integrated in like a circle around a current carrying wire, so when you have got one complete circle, the electric field, the sum of the electric fields there, is equal to the negative changing electric flux. Or this here, remember, is an EMF because this is a voltage. E dx or E ds is voltage. So the integral of E dx, the rate of change of the electric field with respect to position, is voltage, which again is EMF, kind of the same sort of term. And then that's equal to the negative change of magnetic flux. Working on all that. If you have a bunch of coils, you have to multiply it by the number of coils. So here we've got a bunch of coils here. So that's where you get this N term, however many coils there are. I'd love for you to look through the kind of examples of a DC generator and AC generator. Actually, let's go back to those. A generator is going to have this coil here in a permanent magnetic field, and it's connected to this brush. And so as it turns, it will create a current in this wire. Now the current would try to naturally change directions, except it's got this gap here, so there's only one polarity available for the current through here. So the EMF does this. If you have an AC generator, you don't have that gap, and so every time you make a half turn, the polarity changes because the current goes one way, and then it goes the other, and then it goes one way, and then it goes the other, and then it goes one way, and then it goes the other, because it's continually trying to keep this magnetic field constant, magnetic flux constant. So that's where you get up and down, up and down, up and down. It's also pretty much what happens with a motor. A motor that's already turning will have something called a back EMF, because the turning will create a magnetic field, and then that changing magnetic flux will create something, so you get a back EMF, which opposes the motion. And that's what we're going to talk about with inductance a lot. Is what is that back EMF there? All right, so we've got Faraday's law, so that you get an induced voltage because of a changing magnetic flux. Not because of flux, but a changing flux. Lenz's law kind of defines the direction of that again. And then this motional EMF you should be familiar with. This is that bar moving and increasing or decreasing the area that's enclosed by that circuit. Y'all should be familiar with that one. It's the same thing, just using voltage as in terms of E dx. All right, that's the end of this video. We're going to go through one with inductance and inductors and LR circuits. And then that will be the end of the concepts for electricity and magnetism.